Hello, it's Keith here, and this is lesson 52 of the platform-specific series of my 68000 assembly programming tutorials. We're looking at Mintile today, which is my multi-platform software tile map. We're looking at the Atari ST, so here is Mintile running on the Atari ST. So we've got our character moving across the screen. We can X-flip our character. Mintile does not support Y-flip. A future version known as Max-Tile has far more functionality. This is just the basic version, which was written for my Chibi Fighter Street Fighter parody on the 8-bit systems, and that only required X-flip, so that was all the functionality that was put into this version. So what we're going to look at today is the code for the platform-specific Atari ST code, which is the drawing routines, basically. I'm going to look at the joystick reading and things like that. They've been covered in this simple series before, so that's what we're going to take a look at. Okay, let's go over to our source code and let's take a peek then and see what we've got. Okay, so we're looking at the file AST Mintile today, and this is the code for today's example. Now, what we're going to basically do is we are going to define our screen memory. We've got it defined here, and we've got this screen memory address here, and screen base is actually the address of our screen base, and we're going to be using that in our code when we need to draw the entire tile map. Now, there will be times that we need to draw the smaller sprites, and they're actually drawn with the exact same code as the tile map. Now, here is the tile map background data. This is actually a cache of changes. Mintile, because it's designed for 8-bit systems, doesn't use a double buffer by default. And so the tile map background is actually a set of changes, and these are changed back to 0 when the drawing has been done. That's for the background, but the sprites work slightly differently. Here's a sprite. This is the Chibico character that you saw before moving around the screen. There it is. And that's this character here. Now the zeros in here are actually transparent parts. These zeros at the bottom are around the legs, and that's the corner of the sprite that don't have any tiles drawn to them. So the 0 in there has a special function, and we'll see that later. Now, when we want to draw our sprites to the screen, we need to calculate the start drawing position. You see, the way Mintile works is we draw our objects, whether it's the entire screen or a sprite, in strips horizontally. The multi-platform code, which has its own tutorial series, there's a whole tutorial series on the website and videos for that, but the multi-platform code will call multiple executions of do strip, and each one of those will draw one horizontal strip and then move down. So to draw the sprite with that, we need to calculate the top left corner of the object, and get screen pos will do that for us. Now we take an X and a Y coordinate in D1 and D4, that says D2 and D4 and D2, that's completely wrong. Keep making typos, making too many of these too quickly. And so what we're going to do is we're going to calculate the X and Y position. Now, the important thing to notice about the Atari ST is the Atari ST and the Amiga are in a lot of ways very similar in the screen depth, the color resolution, and the potential, and the way that they sort of work in bit planes, but the layout of the screen memory is very different on the Atari ST compared to most other systems, if not all of the systems. It works in bit planes, but basically it works in pairs of bytes, so it's sort of, I'd call them word bit planes, if that makes sense. So bit planes, of course, are that all of the bit zeros of our pixels are in one block, and all the bit 1s are in one block, and all the bit 2s are in one block, and all the bit 3s are in one block. Bits 0 to 3, of course, give us 16 colors. Now, the thing with the Amiga is that basically 16 consecutive pixels will have one word, 16 bits, for one bit plane, and those are actually clustered together. So 16 pixels will use 4 consecutive words in memory, and so that makes things a little bit tricky for working with our bit planes and our screen memory. So basically what we're going to do here is we're going to take our coordinate in tiles, and then we're going to basically multiply that by 2, and that will be the offset in words, and that's what we're doing here. Now, I should point out my coordinates are in logical units, which is pairs of pixels. That's a convenience for the 8-bit systems, where my 256 wide pixel screen needs a logical coordinate of less than 256 so I can crop the screen. So basically we are working in pairs of pixels there, and that's why we're shifting by 2 to the right to convert to a number of tiles here. Now, because the bit planes work in pairs of bytes, each tile is offset depending on whether it's an odd tile or an even tile. So here we're getting the offset in words here, and we're storing that in D1, and then here we're getting the offset in bytes, and we're storing that in D3. We're then basically multiplying the value in D1 and calculating the offset within the bit planes, because as I say, 4 consecutive words are the bit planes for 16 consecutive pixels, and so that's why we're taking that value there and effectively multiplying it by 4 there to get the offset to the correct number of bit planes, and then we're adding the byte offset here, effectively selecting if we are using the first half of the word bit plane for the even bytes or the second half for the odd bytes, and we will have to move across accordingly there. So that's what we're doing there. We're also centering the screen. We're not using the full screen. Again, we're working in a 256 pixel wide screen, but our screen is actually larger than that, so we're centering that. And then we are calculating the y coordinate, which is far easier to work with than the x coordinate because of the memory layout. The Atari ST memory layout is weird. However, it's not really any harder to work with than any other bit plane based screen. It still makes per pixel movement quite hard. It doesn't make a whole lot of difference, but as I say, that's what we've got to work with basically, so that's what we're doing. Now, our do strip routine will be executed and it will be passed parameters for the source tilemap data, the tile pattern bitmap data, the VRAM destination, and the width of the line in tiles, and we're going to then process that. So we're loading in our tile number here, and if that's 0, there's nothing to draw. It's either transparent or it's been drawn before and it's been zeroed in the cache. We're then checking the tile clear flag, and if that is set, we are basically going to clear the tile that we've just drawn, or we're about to draw rather, and that's for when we're drawing the cache to the screen. We wouldn't do that for the sprites. We're then going to calculate our source pattern data. We basically multiply the tile number by 32 and we add it to the source offset in A5 here. What we're then going to do is we're going to move to the next tile in the source tile map, and we're then going to start drawing our data to the screen. So what we're going to do is we're going to basically calculate, we load D1 with 7 because we're going to do 8 lines, and we're going to use DBRA, which in processes for 0. So we subtract 1 from the count we want to do. 8 minus 1 is 7, so that's why we're loading 7 there. And what we're basically then going to do is we're going to transfer the 4 bytes of our pattern for the current line to the respective memory addresses for those pixels with the 4 bit planes. And so the first one is just as offset 0, but then because there's 2 words for each bit plane aligned in memory, we then offset by 2 for the first bit plane, 4 for the second bit plane, and 6 for the third bit plane, and then we've done all 8 pixels for one line. We then move down a line by adding 160 to our VRAM destination, and we repeat until we've done all 8 lines there. Once we've done that, we then want to move across one tile in VRAM. So we're adding 1 to A6 here. But as I said before, we have this weird memory layout. And so if we're at this position here and we add 1, well, we've actually shifted into the wrong memory address because we're now in a different bit planes data. And so what we need to do is we need to skip another 6 bytes to move to the 0 bit plane of the next cluster in memory there. And so that's exactly what we're doing here. We are moving across 6 bytes if we are in the wrong position there. We then decrease D7 and we repeat until we've done an entire line, and that's how we draw a line unflipped to the screen. Only a little bit tricky because of those bit planes, and as I say, it's always a bit difficult with bit planes, I find, for this kind of per pixel movement. So there we go. So that's what we've got. Now, what about when we're X-flipping our data? Well, one solution to that would simply be to have a second copy of all the pattern data that's been X-flipped. Be perfectly possible on a 16-bit system. Wouldn't really be any disadvantage to it. We've got so much memory, but I wanted to do the same as I've done on the other systems on the 8-bits where I can. And what I've been doing on the other systems is building a lookup table that calculates the flipped equivalent in real time. And it's very fast and it doesn't take much memory, so why not do it on the 16-bit systems if the 8-bits can do it? So that's what I've done. So we're loading the address of our flip lookup table, which has 256 bytes. And what we're going to do is we're going to calculate every possible source byte and its flipped equivalent, all 256 of them. So what we're going to do basically is we're going to use D1 as an offset, and as well as an offset is going to be the source byte. And so we're loading that source byte into D0 here, and we're going to shift all of the 8 bits using D3 as a counter here, again using DBRA, so it's loaded with 7, but it actually executes 8 times. And what we're going to do is shift each of the bits out of the right of D0 and back into the left of D2. So after we've done this 8 times, D2 is now the bit flipped equivalent, which we load into A0, our lookup table, and then we increment our lookup table. We add 1 to D1 in bytes, and when that resets back to 0 after 256 executions, we've built our lookup table. we've got our lookup table, but how do we use it? Well, it's pretty straightforward. We've got this alternate version called do strip reverse. Now, this is almost identical to the original one. The only difference is it still draws from left to right, but it works for the tilemap in right to left, so it works backwards. And so we're subtracting 1 from our source tilemap memory address. The memory address is pre-calculated by the multi-platform code, so please see that multi-platform tutorial if you need to know how that works. So we've got our tilemap moving from right to left, and we are calculating our source pattern data in exactly the same way as before, because it is the same source pattern data. When we want to draw it to the screen, though, we now need to flip it via that lookup table. So we're loading A1 with the address of our lookup table. We then load in the byte from A3, our source pattern data, into D0, but we don't write that straight to the screen. What we do is we use that source byte as an offset within our lookup table, and because of the way we've configured our lookup table, the byte we read in from that lookup table will be the flipped equivalent of the source byte here. So after this line, D0 now contains the flipped equivalent, the X-flipped equivalent, which we write to the screen. So we've just X-flipped one source pattern data and written it to the screen here in just 3 commands, and that's pretty quick. We couldn't combine these two together because of the available memory modes, but let's say this is still very quick. So that's done 1 bit plane. That's that's bit plane 0 up there, that's bit plane 1, bit plane 2 and bit plane 3. We've done all the bit planes, we move down the line and we repeat almost exactly the same as before. So as I say, I think using a lookup table, it was the best solution on an 8-bit system. I still think it's the best solution on a 16-bit system, because we've got so much processing power on these systems that a trivial little operation like that isn't going to hurt anything. So that's what I think we should do. So there we go. As you always say, go to the website, learn the source code, the build scripts, and please use this in any way you can, even if somehow you manage to do something commercial. Go ahead and do it. Anyway, as I say, I'm doing a future version that's going to be far better than this, known as Maxtile. Maxtile supports X-flip as well as Y-flip and XY-flip. It supports simple transparency, cutout type transparency. It also supports fast filling and double size, which is something that's quite handy on the 8-bit systems where memory and performance isn't such an option. And as I say, I'll be porting it to everything as I always try to. So if you want to see more, please stick around for that, and hopefully I'll have smoother movement horizontally as well. I'll try and get that done on the Atari ST next time. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.